We live in a universe filled with wonders. From the swirling galaxies to the tiniest atoms, there's an underlying energy that connects us all. This energy, often invisible to our eyes, plays a crucial role in shaping our world. This is the captivating story of radioactivity. The story begins in 1896 with Henri Becquerel, a French physicist who stumbled upon a mysterious phenomenon while studying uranium salts. He discovered that these salts emitted invisible rays that could darken photographic plates, even in complete darkness. This was a groundbreaking observation, hinting at a hidden world of atomic activity. Marie Curie, a pioneering scientist, took up the mantle and coined the term radioactivity. She dedicated her life to unraveling the secrets of this invisible force, discovering new radioactive elements like polonium and radium. Her work not only earned her 2 Nobel Prizes but also laid the foundation for our understanding of the atom and its incredible power. Radioactivity is essentially the spontaneous decay of certain unstable atomic nuclei. These unstable atoms, like tiny restless souls, seek a more stable configuration by shedding energy in the form of radiation. It's a natural process happening all around us, a constant hum of activity at the heart of matter itself. Imagine a tiny cannon firing different types of projectiles. That's a simplified way to visualize the 3 main types of radiation: alpha, beta, and gamma. Alpha radiation is like a cannon firing heavy but slow-moving cannonballs. These cannonballs are actually helium nuclei consisting of 2 protons and 2 neutrons. They have a positive charge and due to their size can be easily stopped by a sheet of paper or even our skin. Beta radiation is akin to firing lighter, faster projectiles. These are electrons or positrons much smaller than alpha particles and carry a negative or positive charge respectively. They can penetrate further than alpha particles, passing through paper but stopped by a thin sheet of aluminum. Finally, gamma radiation is like firing pure energy, high-frequency electromagnetic waves. These waves are massless and travel at the speed of light, possessing the highest penetrating power of the 3. Stopping gamma rays requires much denser materials like lead or concrete. Radioactive decay isn't a chaotic process. It follows a specific rhythm, a mathematical dance governed by the concept of half-life. Imagine a room full of dancers, and every hour half of them leave. This is similar to how radioactive atoms decay. The half-life of a radioactive isotope is the time it takes for half of its atoms to decay into a more stable form. This decay rate is constant and unique to each radioactive isotope. Some isotopes have half-lives of seconds, while others have half-lives spanning billions of years. This decay follows an exponential law, meaning it doesn't happen at a steady linear pace. If we start with a certain amount of a radioactive substance, after one half-life, we'll have half left. After another half-life, we'll have half of that remaining half, and so on. It's like repeatedly folding a piece of paper in half. With each fold, the remaining portion gets smaller and smaller. Radioactivity isn't something confined to labs or nuclear reactors. It's woven into the very fabric of our universe. We encounter both natural and artificial sources of radiation in our daily lives. Our planet is constantly bombarded by cosmic rays, high-energy particles from the sun, and deep space. These rays interact with our atmosphere, creating a shower of secondary radiation that reaches the Earth's surface. Even the Earth itself is naturally radioactive, containing elements like uranium, thorium, and potassium-40 in its crust. Certain rocks and minerals like granite contain higher concentrations of radioactive elements, leading to increased radon levels in some areas. Radon, a colorless, odorless gas, is a significant source of natural radiation exposure. Beyond natural sources, humans have harnessed the power of the atom, leading to artificial sources of radiation. Nuclear power plants, while providing clean energy, produce radioactive waste that requires careful management. Medical procedures like X-rays and cancer treatments also utilize radiation for diagnosis and therapy. Section 5. A double-edged sword: radiation and human health. Radiation, like many powerful forces in nature, is a double-edged sword. It can be both beneficial and harmful, depending on the type of radiation, the dose, and the duration of exposure. Our bodies are equipped to handle low levels of radiation, like those encountered naturally in our environment. However, high doses of radiation can damage cells and DNA, leading to various health problems. The effects of radiation exposure can range from mild burns to radiation sickness, and even an increased risk of cancer. It's crucial to emphasize that radiation is a manageable risk. Just as we take precautions to protect ourselves from the sun's ultraviolet rays, we can minimize our exposure to harmful radiation through safety measures. This includes limiting exposure time, maintaining distance from radioactive sources, and using shielding materials. Section 6. The power of the atom. Radioactive applications. While the potential dangers of radiation are real, it's essential to remember that radioactivity also holds immense power for good. We've harnessed this invisible force to improve our lives in countless ways. In medicine, radioactive isotopes are used for diagnosis and treatment. Medical imaging techniques like PET, or positron emission tomography, scans rely on radioactive tracers to visualize and diagnose diseases. Radiation therapy uses targeted beams of radiation to kill cancerous cells and shrink tumors. Beyond medicine, radioactivity plays a vital role in various industries. In archaeology, carbon-14 dating helps determine the age of ancient artifacts, providing valuable insights into our past. In agriculture, radiation is used to sterilize food products, extending their shelf life and reducing food waste. Even in space exploration, radioactive isotopes provide a reliable source of power for spacecraft venturing far from the sun. These applications are a testament to the incredible potential of radioactivity when used responsibly. Section 7. Seeing the unseen, detecting and measuring radioactivity. Radioactivity, by its very nature, is invisible to our senses. We can't see it, smell it, or taste it. So how do we detect and measure this invisible force? This is where the ingenuity of scientific instruments comes into play. One of the most common instruments used to detect radiation is the Geiger-Müller counter, often depicted in popular culture as a device that clicks when exposed to radiation. This instrument works by detecting the ionization caused by radiation when it interacts with a gas inside the counter. Other detectors, like scintillation counters, rely on the fact that certain materials emit light when struck by radiation. By measuring the intensity of this light, scientists can determine the amount of radiation present. These instruments, from handheld detectors to sophisticated laboratory equipment, allow us to see and quantify the invisible world of radioactivity. Section 8. A responsible future. Managing the invisible force. As we continue to unlock the secrets of radioactivity, it's crucial to remember that with great power comes great responsibility. The responsible management of radioactive materials is paramount to safeguarding our health and the environment. Proper handling, storage, and disposal of radioactive waste are essential to prevent contamination and minimize the risk of exposure. Robust safety protocols and regulations are crucial in industries that handle radioactive materials, ensuring the well-being of workers and the surrounding communities. Education and public awareness are also vital components of responsible radioactivity management. By understanding the basics of radiation, its potential risks, and the safety measures in place, we can make informed decisions and contribute to a safer future. Section 9. The enduring legacy. Radioactivity's impact on our world. Radioactivity, since its discovery over a century ago, has left an indelible mark on our world. It has revolutionized scientific understanding, fueled technological advancements, and continues to shape our lives in profound ways. From the depths of our planet to the vast expanse of space, radioactivity is an omnipresent force, a constant reminder of the dynamism of our universe. It's a testament to the power of scientific curiosity and the enduring human quest to unravel the mysteries of the natural world. As we move forward, armed with knowledge and a commitment to responsible stewardship, we can harness the power of radioactivity for the betterment of humanity while mitigating its potential risks. The story of radioactivity is still being written, and it's a story in which we all play a part. Written by Neil deGrasse Tyson, we live in a universe powered by nuclear energy. It fuels the stars, those distant suns scattered across the cosmos. This energy comes from the very heart of matter, the atom, through two fundamental processes, nuclear fission and nuclear fusion. Imagine the atom like a tiny solar system. At its center lies the nucleus, a dense core containing protons and neutrons. These particles are bound together by an immense force, the strong nuclear force. It is this force that governs both fission and fusion. Nuclear fission is like splitting firewood. We take a large atom, like uranium, and bombard it with a neutron. This causes the atom to split into smaller atoms, releasing energy in the process. Nuclear fusion, on the other hand, is like igniting a star. It involves fusing two light atoms, such as isotopes of hydrogen, to form a heavier atom, like helium. This process also releases tremendous amounts of energy. Understanding these processes is key to unlocking the secrets of the universe and addressing our energy needs here on Earth. Let's delve deeper into the fascinating worlds of fission and fusion. Nuclear fission, the process of splitting atoms, has been harnessed by humanity for both beneficial and destructive purposes. It is a powerful source of energy, but also carries risks that we must carefully manage. When a neutron strikes a large, unstable nucleus like uranium-235, it causes the atom to become highly unstable. This instability leads to the atom splitting apart, releasing energy in the form of heat and light. Importantly, this fission also releases additional neutrons. These newly freed neutrons can then go on to strike other uranium atoms, creating a chain reaction. This chain reaction is what makes nuclear fission so powerful. It's how we generate electricity in nuclear power plants, but also the principle behind atomic bombs. Despite its power, nuclear fission has drawbacks. The waste products from fission reactions are radioactive and can remain dangerous for thousands of years. Proper storage and disposal of this waste is crucial to protect human health and the environment. Fusion, the process powering the stars, is a different beast altogether. It involves fusing light atoms together to create heavier ones, a process that releases even more energy than fission. In the intense heat and pressure found at the cores of stars, hydrogen atoms are forced to overcome their natural repulsion. They combine to form helium, releasing a tremendous amount of energy in the process. This energy is what makes stars shine. Replicating this process on Earth, however, is a monumental challenge. The temperatures and pressures required are immense, far beyond what we can easily achieve. Despite the hurdles, the potential rewards of fusion energy are too great to ignore. It promises a clean, safe, and nearly limitless energy source. Fission and fusion, while both involving the nucleus of the atom, differ significantly in their processes, energy output, and environmental impacts. Fission, the splitting of atoms, is relatively easy to achieve but produces radioactive waste. Fusion, the fusing of atoms, is much more difficult to control, but generates clean energy with minimal waste. Here's a simple comparison. Fission involves splitting heavy atoms and uses uranium or plutonium as fuel, whereas fusion involves fusing light atoms and uses hydrogen isotopes. Fission has a high energy output and produces radioactive waste, while fusion has an extremely high energy output and mostly produces helium, which is inert. Fission carries risks of meltdowns and radiation leaks, while fusion is inherently safer with no chain reaction. Fission relies on limited uranium resources, while fusion has virtually limitless hydrogen fuel. The choice between fission and fusion is a question of balancing risks and rewards. Fission provides a proven, albeit imperfect, solution for today. Fusion, on the other hand, offers a tantalizing glimpse into a cleaner, more sustainable future. Achieving practical fusion energy is one of the greatest scientific and engineering challenges of our time. The conditions needed to initiate and sustain a fusion reaction are extremely demanding. First, we need to heat the fuel, typically isotopes of hydrogen, to temperatures exceeding 100 million degrees Celsius. This is, believe it or not, hotter than the core of the sun. Second, we must confine this superheated fuel, which becomes a plasma, long enough for fusion to occur. This requires powerful magnetic fields to contain the plasma and prevent it from touching the walls of the reactor, which would cool it down and stop the reaction. Overcoming these challenges requires cutting-edge technology, innovative engineering, and a deep understanding of plasma physics. Section 6. A fusion future, powering humanity, protecting our planet. Despite the hurdles, the pursuit of fusion energy is a worthy endeavor. It holds the potential to revolutionize energy production and transform our world for the better. Imagine a future where power plants are fueled by abundant hydrogen isotopes found in seawater. No more reliance on fossil fuels, no greenhouse gas emissions, and no long-lived radioactive waste. Fusion power would be a game-changer for addressing climate change and ensuring a sustainable energy future for all. It could power our cities, industries, and transportation systems, all while minimizing our impact on the planet. The realization of this vision may still be decades away, but the potential benefits are too great to ignore. Section 7. The unending quest, fusion research and its promise. Scientists and engineers around the world are working tirelessly to unlock the secrets of fusion energy. Major research efforts like the International Thermonuclear Experimental Reactor, or ITER, are pushing the boundaries of plasma physics and engineering. ITER, a massive collaboration between 35 nations, is building the world's largest tokamak fusion reactor in southern France. This ambitious project aims to demonstrate the feasibility of fusion power and pave the way for future commercial reactors. Alongside ITER, numerous other research projects are exploring alternative fusion approaches, constantly refining our understanding and bringing us closer to a fusion-powered future. Section 8. A universe of energy, reflecting on the power within. From the distant stars illuminating the night sky to the potential power plants of tomorrow, nuclear energy is an awe-inspiring force. Understanding the processes of fission and fusion allows us to grasp the fundamental workings of the universe and explore solutions to some of humanity's greatest challenges. As we continue to unlock the secrets of the atom, we move closer to harnessing the power of the stars for the benefit of humankind and the planet we call home. The journey is long and challenging, but the rewards are immeasurable. The universe is a vast and mysterious place filled with unimaginable power. It is up to us to unravel its secrets and use our knowledge wisely. We are visual creatures. We rely on light to navigate our world. Light enters our eyes and allows us to see the world around us. But there's another world out there, a world we can't see, a world of radiation. Radiation, unlike light, is invisible to our eyes. We can't see it, smell it, or taste it. Yet it's all around us. It comes from the sun, from space, and even from within the Earth itself. Just like our eyes detect light, we have invented tools to detect radiation. These tools are called radiation detectors. They act as our eyes to this unseen world, revealing the presence and intensity of radiation. Understanding radiation and how we detect it is crucial. It allows us to harness its power for good while protecting ourselves from its potential harm. Radiation detectors are essential tools in numerous fields. They are our silent guardians, protecting us from the unseen dangers of radiation. In medicine, radiation detectors are critical for diagnosing and treating diseases. X-rays, kinetic scans, and PET scans all rely on radiation detectors to create images of our internal organs and bones. These images help doctors identify problems and develop treatment plans. Nuclear power plants use radiation detectors to monitor radiation levels and ensure the safety of workers and the surrounding environment. Detectors act as an early warning system, alerting personnel to any leaks or abnormalities. Environmental scientists rely on radiation detectors to monitor radiation levels in the environment. They can detect radioactive materials in the soil, water, and air, helping us understand and minimize our impact on the planet. Even in industry, radiation detectors play a vital role. They are used to inspect welds, gauge the thickness of materials, and ensure the quality of products. These applications help maintain high standards of safety and efficiency in various industrial processes. Security agencies utilize radiation detectors to detect and prevent the illicit trafficking of radioactive materials. These detectors are vital for safeguarding borders and maintaining national security. Radiation detectors are ingenious devices that can detect the invisible. They come in various forms, each employing a unique mechanism to unveil the presence of radiation. One of the most recognizable radiation detectors is the Geiger counter. This device uses a gas-filled tube to detect radiation. When radiation enters the tube, it ionizes the gas, creating an electrical current that triggers a click sound or a reading on a meter. Ionization chambers operate similarly to Geiger counters, but are more sensitive to low levels of radiation. They measure the electrical current generated by ionization in a gas-filled chamber, providing a quantitative measure of radiation exposure. Scintillation counters utilize materials that emit light when struck by radiation. This faint light is then amplified and converted into an electrical signal, allowing for the detection and measurement of radiation. Semiconductor detectors employ materials like silicon or germanium to detect radiation. When radiation interacts with these materials, it creates electron-hole pairs, generating an electrical signal proportional to the radiation energy. Each type of detector has its strengths and limitations, making them suitable for specific applications. Choosing the right detector depends on factors like the type of radiation, the required sensitivity, and the intended use. Section 4. The science of detection. From interactions to signals. Radiation detectors work by exploiting the fundamental interactions between radiation and matter. When radiation encounters matter, it can interact in various ways, depending on its type and energy. One common interaction is ionization. Ionizing radiation such as alpha particles, beta particles, and gamma rays can knock electrons off atoms, creating ions. This ionization process is the basis for detectors like Geiger counters and ionization chambers. Another interaction is excitation. When radiation interacts with certain materials, it can excite their atoms, causing them to emit light. Scintillation counters capitalize on this phenomenon to detect radiation. Semiconductor detectors rely on the creation of electron-hole pairs. When radiation interacts with a semiconductor material, it can free electrons from their atoms, creating mobile charge carriers that generate a measurable electrical signal. The effectiveness of a radiation detector depends on several factors, including its sensitivity, efficiency, and energy resolution. Sensitivity refers to the detector's ability to detect low levels of radiation. Efficiency is the percentage of radiation that interacts with the detector. Energy resolution describes the detector's ability to distinguish between radiation of different energies. Section 5. Ensuring accuracy, calibration, and radioactive sources. Just like any measuring instrument, radiation detectors need to be calibrated to ensure accuracy. Calibration involves comparing a detector's readings to a known standard. Radioactive sources with known activities and emission energies are used for calibration. These sources emit radiation at predictable rates, allowing for the accurate calibration of detectors. Common radioactive sources used for calibration include cesium-137, cobalt-60, and americium-241. These sources emit different types of radiation with specific energies, enabling the calibration of detectors across a range of applications. Regular calibration is essential to maintain the accuracy and reliability of radiation detectors. Calibration procedures vary depending on the type of detector and its intended use. Section 6. Radiation detection in action, from medicine to security. Radiation detection plays a critical role in various fields, safeguarding our health, environment, and security. In medicine, radiation detectors are indispensable tools for imaging, diagnosis, and treatment. X-ray machines use radiation detectors to create images of bones and internal organs, aiding in the diagnosis of fractures, infections, and other conditions. Radiation therapy, a common cancer treatment, relies on radiation detectors to deliver precise doses of radiation to tumors while minimizing damage to surrounding healthy tissues. Environmental monitoring heavily depends on radiation detectors to assess the levels of natural and man-made radioactivity in the environment. These detectors help identify potential sources of contamination and ensure the safety of our air, water, and soil. In the nuclear industry, radiation detectors are crucial for monitoring radiation levels in and around nuclear power plants. They provide real-time data on radiation exposure, ensuring the safety of workers and the surrounding communities. Detectors also play a vital role in the safe handling and disposal of nuclear materials. Security agencies utilize radiation detectors to prevent the illicit trafficking of radioactive materials. These detectors are deployed at border crossings, airports, and seaports to detect and intercept potentially dangerous materials. Section 7. A safer future. The enduring importance of radiation detection. Radiation detection is an essential aspect of our modern world. It allows us to harness the benefits of radiation while protecting ourselves from its potential harms. As technology advances and our understanding of radiation grows, the importance of radiation detection will only continue to increase. From medical breakthroughs to environmental protection and national security, radiation detection plays a vital role in shaping a safer and more secure future. The ongoing development of new and improved radiation detectors will further enhance our ability to detect, measure, and understand radiation, leading to advancements in various fields. As we venture further into the realms of science and technology, radiation detection will remain an indispensable tool, guiding us towards a brighter and safer future. Nuclear energy is a powerful source of energy. It can generate a lot of electricity. But it also comes with risks. We need to understand both sides. This is important for our future. Nuclear power plants use fission to create energy. Fission is the splitting of atoms. This process releases a tremendous amount of heat. This heat is used to produce steam. The steam then turns turbines to generate electricity. The use of nuclear energy is controversial. Some people support it. They argue that it is a clean and efficient source of power. Others are concerned about the risks. These risks include accidents and the disposal of nuclear waste. We need to carefully consider all aspects of nuclear energy. This includes its benefits and its dangers. By understanding the science and the issues, we can make informed decisions about its role in our energy future. At the core of every nuclear power plant lies the reactor. Think of it as the heart of the operation. This is where the magic of nuclear fission takes place. It's a controlled process that generates an immense amount of heat. The reactor's primary role is to initiate and sustain a chain reaction. This reaction occurs when uranium atoms split. The splitting releases neutrons. These neutrons then cause other uranium atoms to split, and so on. The heat generated in this process is used to heat water. The water turns into steam. This steam drives turbines connected to generators, and that's how we get electricity from nuclear energy. Controlling the chain reaction is crucial. If it's not controlled properly, it could lead to a meltdown. This is a dangerous scenario. That's why reactors have various safety systems in place. Nuclear reactors are complex structures. They consist of several key components, each with a specific function. These components work together to ensure a controlled and safe chain reaction. First, we have the fuel rods. These rods contain the nuclear fuel, usually uranium. The fuel rods are where the fission process actually occurs. They are designed to withstand high temperatures and radiation. Then, there are control rods. These rods are made of materials that absorb neutrons. By inserting or withdrawing these rods, we can control the rate of the chain reaction. The moderator is another crucial component. Its role is to slow down the neutrons. This makes them more likely to cause fission. Water is commonly used as a moderator in many reactors. Finally, we have the coolant. The coolant absorbs the heat generated by the fission process. It prevents the reactor from overheating. Water is also often used as a coolant, circulating through the reactor core. Not all nuclear reactors are the same. There are various types, each with its own design and characteristics. Some are more efficient, others are considered safer. One of the most common types is the pressurized water reactor, or PWR. In a PWR, water is used as both the coolant and the moderator. The water is kept under high pressure to prevent it from boiling. Another common type is the boiling water reactor, or BWR. In a BWR, the water coolant is allowed to boil within the reactor core. The steam then directly drives the turbines. There are also more advanced reactor designs, such as pebble bed reactors and molten salt reactors. These designs offer potential advantages in terms of safety and efficiency. They are still under development. The choice of reactor type depends on various factors. These factors include cost, safety considerations, and the intended use of the generated electricity. Section 5. The nuclear fuel cycle, from mining to disposal. The nuclear fuel cycle encompasses all the steps involved in using nuclear energy. It starts with mining uranium and ends with the disposal of nuclear waste. The first step is uranium mining. Uranium ore is extracted from the ground and then processed to increase its concentration. This process is similar to mining other metals. The enriched uranium is then made into fuel pellets. These pellets are stacked into fuel rods, which are used in nuclear reactors. This is a complex manufacturing process. After spending some time in the reactor, the used fuel rods are removed. They are highly radioactive and need to be handled carefully. This used fuel is either stored or reprocessed. Reprocessing can extract usable material from the used fuel. However, reprocessing itself can create additional waste. The final step is the safe disposal of the remaining nuclear waste, which remains radioactive for a very long time. Section 6. Safety first. Measures to prevent nuclear accidents. Nuclear reactors are designed with multiple safety measures to prevent accidents. The goal is to contain the radiation and prevent its release into the environment. One important safety feature is the reactor vessel. This thick steel vessel houses the reactor core. It is designed to withstand high pressure and temperature. The containment building is another crucial safety barrier. This reinforced concrete structure surrounds the reactor vessel. It is designed to contain any radioactive material that might be released in an accident. Emergency core cooling systems are in place to prevent meltdowns. These systems can flood the reactor core with coolant in case of an emergency. Furthermore, strict regulations and rigorous safety protocols are enforced throughout the nuclear industry. This helps to minimize the risk of human error. Section 7. The Nuclear Dilemma. Weighing the benefits and risks. Nuclear energy presents both significant benefits and potential risks. Understanding both sides is crucial for making informed decisions about its use. One of the main benefits is its low greenhouse gas emissions. Unlike fossil fuels, nuclear power plants do not produce carbon dioxide during operation. This makes it a relatively clean energy source. Nuclear power plants also have high energy output. They can generate a lot of electricity from a relatively small amount of fuel. This makes them efficient and reliable sources of baseload power. However, there are also risks associated with nuclear energy. One major concern is the risk of accidents. While rare, nuclear accidents can have severe consequences, as seen in Chernobyl and Fukushima. Another concern is the disposal of nuclear waste. This waste remains radioactive for thousands of years and requires careful management and disposal to prevent environmental contamination. Section 8. The Future of Nuclear Power. Innovation and Advancements. The future of nuclear power depends on continuous innovation and technological advancements. Researchers are exploring new reactor designs and fuel cycles to improve safety and efficiency. One promising area is the development of small modular reactors, or SMRs. These smaller, more scalable reactors offer potential advantages in terms of cost and safety. Another area of research is the development of Generation 4 reactors. These advanced reactor designs aim to be even safer, more efficient, and produce less waste. Furthermore, there is growing interest in nuclear fusion as a potential energy source. Unlike fission, fusion does not produce long-lived radioactive waste. However, fusion technology is still in its early stages of development. Continued research and development in these areas will shape the future of nuclear power and its role in the global energy mix. Section 9. Conclusion: Nuclear energy in a changing world. Nuclear energy remains a complex and controversial issue. It offers the potential for clean and reliable electricity generation. However, it also poses risks that cannot be ignored. As we transition to a more sustainable energy future, the role of nuclear power will continue to be debated. Balancing its benefits and risks will require careful consideration, scientific advancements, and informed decision-making. Ultimately, the future of nuclear power depends on our ability to harness its potential while addressing its challenges responsibly. This will require collaboration, innovation, and a commitment to safety and sustainability. Section 9. Acknowledgements. The author would like to express sincere gratitude to Professor Dr. Tariq Farooq Nagla for his invaluable scientific contributions and insights on the topics of nuclear fission and fusion. His expertise has been instrumental in shaping this exploration of these powerful forces and their implications for our future.